Now we pose the question, if t equals 2 and t stands for time, how fast is the point moving at this instant? Now what do I mean by how fast the point is moving? Well, when t equals -3, we're about here. By the time t equals 0, we're here. By the time t equals 3, we're here. So as t continuously changes from -3 to 3, we're going to trace out this curve. Now if t is time, at some points in this curve we're going to be moving faster than at others. This is pretty obvious because, for example, this point corresponds to t equals 2, this point corresponds to t equals 3. Between here and here is further than the distance between these 2 points that correspond to t equals 1 and t equals 2. If t is in seconds, that means we move from here to here in a second, and we move from here to here in a second. This distance being greater than this implies that we got to be moving at a greater average velocity between here and here than we are between here and here. Now, the velocity is not going to be constant on any of these intervals. Okay, any interval that you can think of. It's going to be the point is going to be speeding up or slowing down at every point. And we can determine that, we can analyze that mathematically, and we're going to see a little bit about how you do that and what you can get out of the velocity interpretation of motion along a curve that's defined parametrically in terms of time. So, if t is 2 and t stands for time, how fast are we moving at the t equals 2 instant? Well, t equals 2 instant is here. We know we moved this far in the previous second, this far in the next second, so we could kind of average these. Okay, we can get the average velocity here. Just take that distance divided by a second, take this distance divided by a second, average those two results, and we maybe have some sort of an approximation of how fast we're moving, but it's not an answer to the question of how fast is it moving at that instant. Well, if we look at the x and the y, we can determine how fast something would be moving if its x-coordinate, if it was moving along the x-axis according to this rule. Because if x equals t squared, we know that velocity is rate of change of position. If the position is just x and x equals t squared, then the rate of change of the position, which is the derivative of the position with respect to time, gives us the velocity in the x direction. And similarly, the derivative of this function gives us the velocity in the y direction. How is that going to be helpful? Well, let's first calculate the velocity, okay? The velocity in the x direction is the derivative of this, which is 2t. Velocity in the y direction is the derivative of this function, which is just 3. So that if we want to know the velocity, we can actually express that, okay, at any time. And I've expressed that here, at any time. Okay, so here's any old time, well, here's any old value of x, and the time at this point is the square root of the absolute value of x. Okay, so, and it's actually could be plus or minus the square root, the square root of the absolute value of x, but I'm going to use the positive here because we know the time is positive from here to here. Okay, so t is the positive square root of whatever the absolute value of whatever x is at this point. Of course, x in this case appears to always be non-negative, so we don't really need the absolute value, but we want to be careful and think about that, and you should think about that. So I'm not going to go into an explanation of that. That's a pre-calculus idea. The solution of this equation is t equals plus or minus the absolute square root of the absolute value of x. And you really want to be sure you kind of understand that. But that's not where we're going right now. That's just something you need to know. Okay. Well, in other words, if we know the x-coordinate, we can find the t-coordinate. Or if we know the t, then, of course, we don't need to know the x-coordinate. Well, we do if we want to actually locate the point. Okay, so at some time t, the particle is here. This is any arbitrary time t. Then we know that the velocity in the x direction is 2t times the I vector being a unit vector in the x direction. And the y component of the velocity is 3 times the j vector. Again, why? Because velocity in the x direction at time t is 2t. Velocity in the y direction is always 3. Okay, so we have these two components of the velocity, and we add those two components and we get the velocity, both the magnitude and direction. In other words, the magnitude and direction of this velocity vector will be the magnitude and direction of the particle's velocity at the instant when time is t. Now, if we want to find that result for t equals 2, we just plug in 2 and we get the result. Now, I thought I had it down here somewhere, but I don't think I do. Maybe I'll write that in, but you can easily do that. If t equals 2, then 2ti plus 3j is just 4i plus 3j. And that would be the velocity at that instant. And I don't guess that I've actually done that. So anyhow, well, maybe it's there somewhere. Yeah, okay, here it actually is. Okay, so we asked the question now, though. We didn't ask for the velocity, which gives us both the magnitude and direction of our motion, but we asked for the speed. And speed is not a vector quantity. Speed is just the magnitude of the velocity. So to get the speed, we've got to take the magnitude of our velocity. Okay, the magnitude of the velocity is what? Well, Pythagorean theorem tells us that we got 2ti and 3j. The 2t and the 3 form legs of a right triangle whose hypotenuse represents the velocity. So we just take the magnitude of the velocity vector, and everybody I think has had linear algebra, and I'm assuming everybody's had linear algebra and understands these things, except I think there's one person in the class that's just seeing it. So, but it's not a difficult concept. So we have the velocity is the square root of what? The square of the 2t plus the square of the 3. Or, in this case, 4t squared plus 9. So if we want the velocity at t equals 2, we plug in 2 for time. 2 squared is 4. And 4 times 2 squared then is 16. We add 9, we get 25. And the square root of that is 5. So at the t equals 2 instant, this thing's actually moving with a velocity of 5 units per unit of time. 5 units of distance per unit of time. We also mentioned the s of t vector. Okay, that's our position vector. Now, our velocity vector is sketched here with its x and y components. Our position vector just goes from the origin out to the point on the graph. So the position vector is just a vector from the origin to a point on our curve. And that vector is s of t, in this case t squared I plus 3tj. Now it's pretty clear that if I take the derivative of this expression with respect to t, that the t squared is going to give us a 2t, the 3t is going to give us just a 3, so that the derivative of this position function is just our velocity function, 2ti plus 3j. So, we're going to use the velocity function to approach the idea of an arc length. Okay, so in the context of velocity, we're going to look at the arc length of this curve in the next video.